Hello everyone, I am Sunanta from SNS College of Technology, Department of Mathematics. As the continuation of the lecture series in the topic curvature, envelopes and evolutes, now we are going to see a case study based on curvature. So here we are going to see a case study on curvature in railway track design. So here the problem statement is challenges of curvature in railway tracks. The first one is operational risk. So curvature introduces speed restrictions and increases wear on rails and wheels, directly impacting operational efficiency and asset lifespan. Second one is maintenance burden. So higher maintenance costs stem from accelerated track deformation requiring frequent repairs and increasing overall life cycle expenses. Third one is safety concern. Most critically importantly, designed curves elevate the risk of derailment and accident, jeopardizing lives and significant infrastructure. The core challenge lies in designing curves that effectively balances safety, cost and operational efficiency without compromise. Next is understanding curvature and types. So here railway tracks incorporate two primary types of curves to navigate varied terrain and obstacles. First one is horizontal curves and vertical curves. So horizontal curves are changes that track directions horizontally. They can be simple, compound or reverse. So next is vertical curves. These provide smooth transition between different track gradient, ensuring a comfortable ride, preventing excessive vertical forces on rolling stocks. So here clearly we can see the degree of the curvature in this. So here the key metric is the degree of curvature defined as capital D at an angle subtended by a 30-meter chord. Sharper curves exhibit a higher capital D and smaller one radius is r. The relationships is approximated by the formula d equal to 1719 by r, where r is the radius which is taken in meters. Now let us study engineering forces on curved tracks. When a train negotiates a curve, it experiences a powerful centrifugal force that pushes it outward away from the center of curvature. This outward force generates lateral acceleration which, if unchecked, significantly increase the risk of derailment. To counteract this, engineers employ a critical design feature known as super elevation or cant. This involves raising the outer rail of the curve relative to the inner rail, creating a banking effect. Next is calculating super elevation. The core solution method. The precise calculation of super elevation is fundamental to railway safety and efficiency. It is determined by the equilibrium super elevation formula, which is small e equal to v square divided by g capital R into capital G divided by 100, where v is the train's speed, R is the curve radius, G is the track gauge and small g is the acceleration due to gravity. Here when we see an example for 2-degree curve of radius 860 meters and the speed of the train is given as 80 and capital G is given as 1435. So on substituting everything we get E equal to 84 millimeter. This indicates that the optimal height difference between the outer and the inner rail for the specific set of parameters. Next is applying curvature design on a high speed railway section. So consider a real world application on a critical section of a high speed rail line. Location: a hypothetical 5000 feet radius curve within a active high speed corridor. Design speed: this is targeted at 75 meter per hour or 120 kilometer per hour. Next is maximum super elevation limit is set up to 6%, that is 150 millimeter for 1435 millimeter gauge. Next, steps taken. Equilibrium elevation calculation. Using the formula, the ideal E was computed for 120 km per hour and adjustment for can deficiency exists. Since multiple train types with varying speeds use the track, adjustments were made to account for cant deficiency and cant excess to avoid discomfort and excessive wear. The final design selected a practical E slightly lower than equilibrium to accommodate slower trains. Super elevation transition zones. Smooth gradual transition zones were implemented at the entry and exit of the curve to progressively apply and remove super elevation, preventing sudden jolts and ensuring a comfortable ride. Results and benefit of proper curvature design. Enhanced safety. Trains can now safely negotiate curves at their designated speeds, significantly reducing the risk of derailment and ensuring passenger security. Reduced maintenance. Optimized super elevation minimizes lateral wear on both rails and wheels, extending their lifespan and sustainability, lowering maintenance cost over time. Next is improved comfort. Smoother transition into and out of curves coupled with balanced forces lead to a noticeable improvement in passenger comfort. Next is operational efficiency. By eliminating the need for stringent speed restrictions on curves, overall operational efficiency is maintained. Next is challenges and limitations encountered. Physical constraints. Existing infrastructure like bridges, tunnels, and stations often impose limitations on curves, sharpness, and the achievable super elevation, forcing design compromises. Cant deficiency. When full equilibrium cant isn't feasible for all train speeds, designers must manage cant deficiency or excess, necessitating speed restrictions or additional safety measures. Next is environmental factor. Weather condition and challenging terrain can affect the practical implementation and long-term sustainability. Next, lessons learned and engineering best practices are early integration, adherence to standard, continuous monitoring, cross-functional collaboration. So, in early integration, integrating curve design consideration early in project planning is critical to avoid costly rework and ensure optimal track alignment. Next is adherence to standards. Rigorous use of precise calculation and established industry standards ensures the highest level of safety and operational efficiency. Continuous monitoring. Implementing continuous monitoring and proactive maintenance programs is essential to manage wear and tear caused by curvature and preserve track integrity. Cross functional collaboration. Effective collaboration between civil engineers, track designers, and operations termed in paramount for successful project. Next is conclusion. Curvature engineering as a balance of safety, performance, and cost, complex yet critical. Risk mitigation, the proper application of super elevation and precise curve radius calculations are essential for mitigating risk yet enhancing safety and ensuring smooth operation. Real world case studies consistently demonstrate measurable improvement in safety, passenger comfort, and operational efficiency when curvature engineering is executed with precision. Thank you.